Alright, so in this video I'm going to take a look at Unit 2 paper from January 2010. So we're going to start off with some mechanics. So we've got a digital camera and we've taken a sequence of images and the images are taken every 5 seconds. So if this one was taken at time 0, this one's 5 milliseconds later, 10 milliseconds, 15, and so on and so on. Okay, so the ball has a horizontal velocity of 0 at A, okay, and reaches a constant horizontal velocity at D as it leaves the racket. The ball travels a horizontal distance of 0.68 between D and G, so once it's left the racket. Show that the horizontal velocity of the ball between positions D and G is about 45 meters per second. So if we look at how long it's taken, because we're going to do distance and time, we've got 1, 2, 3 sets of 5 milliseconds. So the time taken is 15 times 10 to the minus 3 seconds. The displacement during that time is 0.68 meters. There are no forces acting in the horizontal direction on the ball, so we know the velocity is going to be the same throughout. So we can essentially just use this equation, and we can only use that when we know velocity is constant, or we want the average velocity. So 0.68 divided by 15 times 10 to the minus 3, and then we do that calculation. We get 45 meters per second, which is what we were trying to show in the first place. So that's always nice. Okay, so let's move on to the next question. So the next part wants us to work out what the acceleration was between A and D. So we're going to assume the acceleration is constant here. So the time over which it accelerated is again 3 spacings, so 15 times 10 to the minus 3. If you have a look at it, you'll see there are 3 spacings over which it occurs. The change in velocity is 45.3 yada yada yada. Assuming acceleration is a constant value, we can calculate it using delta V over T. So that's going to be 45.3 blah 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 divided by 0.015, and that comes out with a value of like 3022. So we're going to give that as 3.0 times 10 to the 3. 2 significant figures, which would be an appropriate number here. Okay, so at D, the ball was projected horizontally from a height of 2.3 meters above the ground. Show that the ball would fall to the ground in about 0.7 seconds. So the key here is the fact it tells you it's projected horizontally, because that means in the vertical direction its velocity is 0. So U is going to be 0. We've got the displacement is going to be downwards 2.3 meters. That's where it's going to fall. We don't know what the final velocity is. The acceleration is downwards 9.81, so I use minus 9.81, and we want to find out what the time is. So we want the Subat equation that doesn't have V in it. So we're going to use S equals UT plus half AT squared. U is 0, so we can immediately get rid of that. So we can get that the time is 2S over A, or square rooted. So we're going to get 2 solutions to this, one of which is negative and makes no sense. So it's going to be 2 times by minus 2.3 divided by minus 9.81, all square rooted, and that comes out as about 0.68 seconds, which is roughly 0.7 seconds there. Okay, so just a quick thing on this. You could have used downwards as the positive direction, in which case you'd have had positive 2.3 and positive 9.81 there, and you can see that those signs would have cancelled each other out anyway, so that's fine too, but I always use downward as negative just so I'm consistent with what I do. Okay, so that's that one right there. Calculate the horizontal distance that the ball will travel after it leaves the racket before it hits the ground. So we know how long that takes because we just calculated it. We know what its velocity is and that its velocity is going to be constant. So we can use this equation as velocity is constant. So it's like 45.3 times by 0.68. I'm always using the unrounded values here. And we get a value if we do this, it's like 30 points, so it's going to be 31 meters to two significant figures there, because that's what the data in the question is. There's quite a range because of answers. This one I think anywhere between about 30 and 32 is fine because you may have rounded at any given stage, but I always use unrounded all the way through. Explain why in practice the ball will not travel this far before hitting the ground. So this is to do with air resistance acting against the motion in the horizontal direction, so the speed will decrease, giving you a smaller distance. So let's get that into written words. Alright, so let's review what we've got. So air resistance will act against the motion of the ball, so it will provide a negative horizontal acceleration, which would act to decrease the horizontal component of velocity, and we saw from the previous part we used that to calculate the distance, so if that decreases, the horizontal distance travelled will decrease as well. Okay, so that finishes question 1. Let's move on to the next one. Okay, so we've got some springs used in suspension on a vehicle, and we have the weight force of the vehicle and how long the vehicle is. We know where the centre of mass or the centre of gravity is when that is unloaded, and there's 4 springs on the vehicle, 1 for each wheel. Okay, so the first thing, this is going to be solved using moments. So the first thing we want to define what moments are. So it's the force times the perpendicular distance from the line of action of the force to the pivot. So let's get that down. Alright, so there's your definition of your moment. Just to quickly explain what that means. So say we're taking the moments, I'm going to draw this up on the top right, taking moments about this point here, and we've got a force here. A line of action is essentially just a line extending your force arrow, so it's parallel and exactly in line with your force, so it's like that. So then your point is here, so your perpendicular distance is that one. That's why it's the perpendicular distance between the line of action and the point, and then this is obviously your force. Let's call that D. So then the moment of that force about that point is F D there, but this is the formal definition you've got down here, and that's what you would need to be able to quote when asked about what moments are. Okay, so let's press on. So state and explain which pair of springs, front and rear, will be compressed the most. So the first thing is, if we take moments about the centre of gravity, the moment of one spring must be equal to the moment of the other if it's in equilibrium. So that's the first thing. So then if the moments are equal but the springs at B are much further away than X, that means the force at B is smaller than the force at A, so the force at the rear will be greater, and it's to do with the distance and moments being in equilibrium. So let's put that down. Okay, so that's what we've got there. I've probably been a little bit more detailed than I would if I was actually answering this question, but I just wanted to make everything very clear. So taking moments about the center of gravity, the moment of the force of the rear spring and the moment of the force of the front spring must be equal to each other if it's in equilibrium. The perpendicular distance from the rear spring to the center of gravity is smaller, so the force must be bigger to give the same moment. That's essentially the principles there. Okay, so let's move on to the next part. So taking moments about axle B, calculate the force exerted on the truck by each rear spring. So let's first do the moment of the weight force of the object. So the weight force of the object is 14,000 newtons and it's at a distance of 1.4 meters from B. And then there will be 2 moments from the rear springs because there's 2 of them, and each one is going to supply a force F, and that's 2.5 meters away from B in the perpendicular direction. So then let's rearrange this first and then we'll solve it. So 14,000 times 1.4 divided by 2 times 2.5, which is 5. And if we solve that, we end up with 3922. So 3.9 times 10 to the 3 newtons, 2 significant figures, which all the data is. So let's stick with that. Okay, so that's your force from each spring. The spring constant of each of these springs is 100,000. And I got that. Calculate the compression. So we're going to be using a rearranged version of Hooke's law. Force divided by K gives you the extension. So each one has a force of 3922 using unrounded. They have a spring constant of 100,000. So then we can see that we're going to end up with 3.9 times 10 to the minus 2 meters as the compression of each spring, or change in length of each spring. Okay. The springs must not be compressed by more than an additional 0.065. Calculate the maximum load that can be placed at point X, which is directly above the center of the rear axle A. Okay, so let's first work out what the additional force would be. The moment of this additional force as well. So the maximum force we could put on would be the spring constant times X. So it would be 100,000 times by 0.065. That would be your additional load, which is 6,500 newtons. But there are 2 springs it's shared out, so max force, weight force, oh blimey, let's try it again. Max force is going to be 2 times by that, which is 13,000 or 1.3 times 10 to the 4 newtons there. Okay, so that's that one there. So just to recap, using the additional extension, we can work out how much additional force each spring can take. And then because there's 2 springs, that means we can put a load of twice that amount on the whole thing. So that finishes question 2. Let's move on to the next question. Okay, so we've got a cross-sectional look at an optical fibre. So we're going to be looking at some refraction and TIR by the looks of it. So the first thing they want to do is name the parts A and B of the fibre. So that's what we've got there. So A is on the outside, so that's your cladding. B is on the inside, so that's your core. Really straightforward there. All right. On figure 3, draw the path of the ray of light through the fibre. Assume the light ray undergoes total internal reflection at the boundary between A and B. Okay, so the first thing is it's starting off in air. So whenever your core is, must be higher refractive index than air. So it's going to bend towards the normal. So that's what we've got there. Apologies that I can't really do straight lines very well on this device, but that should be showing it bending towards the normal. Then what we'll see is it reflecting off this boundary, and your angle of incidence should equal your angle of reflection, so it should be a roughly symmetrical bounce. So it'll look a little bit something like this. So that's where your 2 marks are, one for showing it bending towards the normal as it enters the optical fibre, the other one for showing angle of incidence equal to angle of reflection for TIR. Calculate the critical angle for the boundary between A and B. Give your answer to an appropriate number of significant figures. So we've got the 2 refractive indices. So obviously the critical angle is when the angle of refraction is 90 degrees. So N1 sine theta critical is equal to N2, because it's multiplied by sine of 90, which is 1. So the critical angle is N2 over N1, so that's 1.48. No, it isn't. This is inside. So it's going from, if we look at the diagram, where's it going from? Going from B into A. So N2 is 1.46, N1 is 1.48, because going from B into A. So, and then we want to take the inverse sine of that to calculate it. And if we do that, we end up with a value of 80.6 degrees, giving it to 3SF because the data is all 3 significant figures. All right, so that finishes that question there. Let's carry on. State and explain one reason why part B of the optical fibre is made as narrow as possible. So the narrowness is all about preventing multipath or multi-mode dispersion, as it's known. And the reason you do it is because you don't want pulse broadening to occur from your different light waves taking different paths to get to the end. So the state part, like why do we have it, is to prevent multipath dispersion. So that's what we've got there. We've got it to narrow to prevent multipath dispersion. And what is that? It's where light waves take different paths to get to the end. So if it's wide, they can take lots of different paths. So the signals arrive earlier or later than expected. So it makes the pulses broader than they were originally when you sent them in. Okay, so that's why we have them narrow. So state one application of optical fibres and explain how this has benefited society. This is a very deep one. All right, so what we use them for, so we use them in communication, so to transmit signals. So those of you who have BT Broad Virgin fibre optic broadband, that's in the name. They use that. You can transmit very high levels of data or high rates of data with them, and it's very, very fast because obviously it's traveling at the speed of light. So that's the application and the advantage. So let's put that into text. So that's what we've got here. They're used for broadband communication lines, and the advantages you get, they're very high speed. You're using light, and you also are able to transmit very large quantities of data using them, both of which are very useful. All right, so let's move on to the next question. Okay, so we've got a side view of a string on a guitar. So we're going to be looking at stationary waves in this question. That's what's going on with the guitar. So it says it can't move about at either bridges, so we've forced A and B to be nodes. When it's vibrating its fundamental mode, the frequency it produced is 108 Hertz. Sketch the stationary wave produced when the string is vibrating in its fundamental mode. So what we should be able to see is half a wave, if you like. So essentially, oh blimey. Okay, so I'm going to just sketch it a bit like this, and then obviously half a time period later it would be at the opposite part of the cycle, so like this. There, so that's your fundamental mode. It's not the best sketch in the world, but it'll do. Calculate the wavelength of the fundamental. So we're looking at half a wave, and that's 0.64 meters long. So it's going to be 2 times by 0.64, which is 1.28 meters. So that's essentially 1.3 meters to the right number of sig figs. Okay, so we've got the frequency 108 and the wavelength. So what do you know? We're going to calculate the speed. So speed is wavelength times frequency. So it's 1.28 times by 108. And if we do that, we get an answer of 138 point blah, 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 blah. So that's going to be 1.4 times 10 to the 2 meters per second to give it to 2 SF. That's appropriate here. All right, so let's move on. While tuning the guitarist produces an overtone that has a node 0.16 from bridge A. Sketch the station wave produced and label all nodes that are present. So nodes are always evenly spaced, so we're going to have one. So we're going to have one here, we're going to have one here, we're going to have one here. So we're going to see essentially 2 full waveforms. It's going to go like this. So we can see 2 full wave cycles there, and then half a time period later it will be at this position here, which I'll show you with a different color. So we've got, and it wants us to label all the nodes. Node, and I realize I missed this one right at the beginning, and a node. So we've produced 5 nodes overall, or 3 between those 2 we've created there. All right. Calculate the frequency of this overtone. So the wavelength is 2 times 0.16, which is 0.32. The speed is going to be exactly the same. So frequency is speed divided by the wavelength. So it was 1.3 yada yada times 10 to the 2 divided by 0.32, giving us a frequency of 4.3 times 10 to the 2 hertz when we round it to an appropriate number of significant figures. Okay, so that's the new frequency. The guitarist needs to raise the fundamental frequency of the string. State one way in which this can be achieved. So I always think of stuff in terms of the equation. So this is the equation for the frequency of your fundamental. So we can see in this equation what we can do to reduce it. We can decrease the length, we can increase the tension, or we can decrease the mass per unit length. So we can, let's put those in now. All right, and just in terms of practically how things work, those of you who've seen guitars or other stringed instruments, you'll see the strings are of different thicknesses, and they get higher the thinner the string gets. That's because you've decreased the mass per unit length. You can tighten them up. Increasing the tension increases the pitch as well. And if you put your finger on a fret, what you do is shorten the string. That's why it sounds higher as well. So that's some guitar related info. Let's finish there and move on to the next question. Okay, so just over 200 years ago, Thomas Young demonstrated the interference of light by illuminating two closely spaced narrow slits from a light from a single source. What did this suggest to Young about the nature of light? It showed diffraction and interference, which are wave properties, so it showed that light was a wave. Okay. So, demonstration can be carried out more conveniently with a laser. A laser produces coherent monochromatic light. So we're just going to define what those two things are. So monochromatic means only a single wavelength is produced. Coherent means all your sources of light have a fixed phase difference. So let's get those down. All right, so those are your definitions for monochromatic and coherent. Let's move on. All right, so state one safety precaution that should be taken when using a light. There are a few things you can suggest here. You can set it up so it points away from where people's eyes are. Don't say stuff like, don't shine in people's eyes. Obviously, you're not going to deliberately shine stuff in people's eyes. You should set it up so that it's not going to happen. You could put a sign up to warn people that there are lasers. You can wear some laser safety glasses as well. So there's a few things we can put, so let's get those down. So those are yours there. The ones that you'd have used in your lab would probably be this first one. So you set it up so it's pointed away. Like obviously when you're doing it in class, everyone knows lasers are being used, so the sign's a bit irrelevant, and laser safety goggles are quite expensive, so it's very unlikely your school has those. So this one is the one that really applies to you and the one you should be thinking about. Okay, so let's move on to the next part. Okay, so we've got a two-slit interference pattern from our monochromatic source. So we've got a slit spacing of 0.3 millimeters, a distance to the screen of 10 meters. Use figure 6 to calculate the wavelength of light used. So we're going to be using W equals lambda D over S. So lambda is WS over D. So it's going to be 0.16 times by 0.30 times 10 to the minus 3 to get it in meters, and we've got 10 meters there, but we've also got 1, 2, 3, 4, 5, 6, 7, 8 spacings being shown, which is 0.16. So that would be, so 0.16 over 8 would give you the spacing between two adjacent ones. And then if we put that into the ordered calculator, we end up with a value of 6.0 times 10 to the minus 7 meters. So you can see that that's in your visible spectrum. So 600 is towards the red end of your visible spectrum there because it's quite long. The shorter end's about 400 or so. Okay, so that's that one there. So the laser is replaced by another laser emitting visible light with a shorter wavelength. State and explain how this will affect the spacing of the maxima on the screen. So let's get our equation back up. So W equals lambda D over S. Let's identify the things that are constant. So we haven't changed the slit spacing, we haven't changed the distance. So what we can see is that spacing and wavelength are directly proportional. So let's get that first. So spacing and wavelength are directly proportional, so a shorter wavelength results in a smaller spacing or maxima closer together. Alright, so that's what we've got there as the answer. So that finishes this question on interference. So let's move on to the next question. Alright, so in this question we're going to describe by experiment how we would determine the Young modulus of a metal wire. This is a practical you should have done as part of the course, so it should be fairly straightforward for you to answer this question. And we've got space for a diagram if we want it. So generally speaking, you would have probably done this, you would have had like a bench going along here, probably a pulley, and then your wire would have been stretched out, hung like this, and then what you do is you hang masses on the end of it and fix that end, and you vary the mass and you measure the length and to get the extension by some mechanism. So that's the general principle how this works. So first of all, let's think about the variables. So what we're going to do is we're going to hang different fixed masses on the end so we can calculate the weight force. So let's put that down first. So we're going to hang, so we've got our variables, so we hang different size masses to give us different loads. I'm suggesting using about 1 kilogram to 7 kilograms to give you significant extension. And what you're going to do is measure the extension using a vernier scale. That would be an appropriate mechanism to measure extension with. Okay, so that's one set of measurements we need to do. Then we're going to need to think about how we can get the cross-sectional area as well. So for that, we'd need a micrometer. All right, so that's the other set of measurements we're going to need to take. So that's the general principle we're going to be doing. So let's look at how we're going to get a graph that we need. So to ensure our readings are as accurate as possible, we're going to take repeat readings of extension and get an average extension for each load, and we want a graph of load versus extension. Okay, so then what we're going to do is we're going to look at our equation for Young modulus is stress over strain. So that's force divided by area over extension, which I'll put as an x, over original length. So if we want to make it load versus extension, we're going to have L equals E Young modulus times cross-sectional area. I don't know why I made L the subject. I'm making force the subject, so we're going to divide by area, and that's multiplied by the extension. So we can see that the gradient of the graph we've plotted will be the Young modulus times cross-sectional area divided by the length. So let's then explain how we're going to get the Young modulus. So that leaves us with how we're going to calculate the Young modulus. Let's make sure that's right. So we're going to multiply the gradient of that graph by the original length, which we can measure just using a meter ruler, and then we can divide that by the cross-sectional area, and that would leave us with the Young modulus of the wire. So there's a couple of things I think we should quickly review that would make this a little bit better. So here I think we should identify with a micrometer. That would make that better. That explains how you're measuring things. And then I think we would be better off if we explained how we get area from diameter. So it's going to be pi d squared over 4. That would improve that section. So I think that section with the cross-section area of the wire could do with some improvement. But other than that, I think that's pretty much fine. Okay, so that's your method to determine Young modulus. So carrying on, we've got a plot of stress against strain here. And draw a best fit line using the data points. This is going to be pretty tricky on this tablet, but let's give it a go as best you can. So it's going to be a straight line to start with, and then it's going to curve off. So okay, so that's the best I can do on this tablet. So we've got a straight line up to around 5 times 10 to the minus 3 on your strain. Then it's clearly curving off. I think I undercut it a little bit than I should have done here, so I'd rather have gone a little bit smoother, but that's the best I can do on this, I'm afraid. Okay, so then I'm guessing we are going to have to work out the gradient. So let's show you that. Where's a nice point I can use? Let's use that one here. So again, my triangle is going to be really rough, I'm afraid. So what that should have been is at this point here is at 4.80. This point here is going to be 4.8. 4.6. So your gradient is going to be a change in y, which is 4.6 times 10 to the 7, and your change in x, which is 4.8 times 10 to the minus 3, which gives us a gradient of around 1 times 10 to the 10 pascals can be the unit, or you could give it in newtons per meter squared, which is the typical unit I would give that in, because it's stress over strain. So that's going to be your gradient, so I'm guessing we're going to have to do that in the next question, so let's have. Alright, so we've done the part where we calculate Young modulus using the gradient, so just look back if you want to see that. After reaching a strain of 7.7 times 10 to the minus 3, the wire is to be unloaded. Sketch the line you would expect to obtain for this. So if we look back at the graph, what your line should do is go parallel to the original straight line, but it's gone past the plastic points, line of deformation. So if this is your original line, what you'd expect to see on your graph is like this, but it should go all the way back to your x-axis there, and obviously actually this one's going to start here. So it'll end up with a final displacement showing it's been plastically deformed, but this section and this section should be parallel to each other there. Alright, so let's move on. It's predicted that the future large offshore wind turbines may have a power output 10 times that of the largest one currently in use. These turbines could have a blade length of 100 meters or more. So this is your classic turbine. Alright, so we've got a wind speed of 11 meters per second. The volume of air passing through the blades each second is 3.5 times 10 to the 5 meters cubed. To show the mass of air is about 4 times 10 to the 5. So we've got density. So the equation we're looking for, mass, is density times volume. So 1.2 times 3.5 times 10 to the 5. If we do that, is going to give us a value of 4.2 times 10 to the 5 kilograms, which is roughly 4 times 10 to the 5 kilograms. So we can see that that works out there. Okay, so it now wants us to calculate the kinetic energy of air that would enter each second. So this is your equation. So let's do half times mass times by the velocity squared. If we do all that and give our answer to 2 cm, we end up with 2.5 times 10 to the 7 joules of energy every second. So that's a pretty sizable amount of energy going on there, 25 megajoules per second. It's predicted that the turbine will produce an electrical power output of 10 megawatts in these wind conditions. Calculate the efficiency of it. So this was the kinetic energy per second, so that's what the theoretically could produce. So efficiency is going to be what it does produce over what it could produce times by 100. We wanted percentage efficiency. So that's going to be a value of 40% efficient, which is okay. It's not great. Most gas power plants are in the 60s sort of percent, so it's not ideal, but solid. State 1, disadvantages and 1 advantage of wind power in comparison to fossil fuel. So the advantages are like no CO2 produced, doesn't use up resources that are going to run out, but it's really intermittent. It is quite unsightly, looks like rubbish, and requires a large amount of expense up front. Okay, so let's get that down. So those are the two that I've picked there as the advantages and disadvantages. Okay, so that completes this paper. I hope you found that useful. If you spotted any errors as you've gone through, please do comment and let me know about them. Likewise, if anything's not quite clear, please do comment and let me know so I can clear them up. But thank you very much for taking the time to watch this. Do look out for the videos I've got coming up going through the other Unit 2 papers, and do make sure you check out the videos I've done for Unit 1, 4 and 5 already to help you with those.